Moving on to the cycles part of the time series model. This is essentially a part one of the cycle analysis video where I will introduce the MA model. MA is short for moving average. Alright, so I'm starting off, we call that a stationary process. In this series, I'll call it the covariant stationary process, is when the correlation is nearly zero. Unrealistically, well, it's unrealistic to think that it will be exactly zero, but correlation is around zero as the order increases. Correlation basically is a way of looking at the movement, because in a time series variable, if we observe trends over time, then there will be autocorrelation. But generally, we will want what we call the white noise, or a time series process with no zero mean, or the constant variance. And so when we have this, we make it very hard to predict the future. But ideally, that's what we want, because if it's easy to predict the future, then we have a very biased and unpredictable or uncertain model. All right. So the Routledge theorem is kind of dissecting the cycles part of the model more mathematically. The cycles can also be known as the residuals, because they're almost as, think of like the remainder of when you take the trend and seasonality out. The trend and seasonality are the most, even visually, the most observable part of the data, whereas the cycles are kind of harder to find. And so when we have this lagged model, we call this error part of the model, where the mean will be around zero. We'll call that the Routledge theorem, because we're measuring the very short-term memory of these leftover patterns. And these leftover patterns is what we're gonna call the moving average model. The data are the ones that represent the coefficients for a moving average. We need to watch out for that, because in the next video, I'm gonna introduce the autoregressive model, and the autoregressive model does not use data coefficients. They use let me quickly check. They use these slanted phi coefficients. Forgot what it's called. I'll look it up later, but remember that the data coefficients are what we will use for the moving average model. So basically, when we take a look at it, it looks like the regression model, except this is specific to just the leftovers / the remainders of the time series data, not the whole thing. The whole thing in the last series, we kind of represented it by like beta 1, y, t, and then like x1, so that's completely different. This is just like the very small part of it. And so even though this model is small, as these coefficients become bigger, we have higher correlation and thus less covariant stationarity. And the easiest way we can kind of observe whether there is a moving average model or not is by the ACF and PACF. And so for the MA model, there usually is one big spike at the ACF of lag 1, and then the all other lags past that will be around 0. And then PACF, it will kind of be like an oscillating, like gradual decrease. And so recall that, well, not recall, but we have to know that the some of all these coefficients here have to be less than 1 if we want the model to be invertible. By invertibility, I mean that we can kind of transition back and forth from the MA model to the AR model, and we can do that so that we can kind of weight the more recent values heavier. Think of like weighted regression, and we need a blue model for in order if we want to weight the coefficients properly. All right, sorry for that. I just needed a cup of water. So yeah, ACF, if the PACF is kind of gradually decreasing in an oscillating way, it doesn't have to be like positive, negative, but if there's a big spike at 1 and then all the other values are close to 0, this should be a little smaller, but if this value is close to 0, all these values are close to 0, then for the ACF and then PACF, we have like not a significant spike, but kind of just a gradual decrease. That's when we know it's a moving average. All right, since most moving average models are only concerned with the first order or first lag, because they're very hard to model, since remember that we're modeling the leftovers, right? Just the very smallest parts of our errors, and so usually we'll only want to forecast one step ahead, and it won't be very specific. It'll be very the forecast will be very general, and it'll be close to the mean, because that's what the MA model is based on. It is based on the mean, and the variance will be very small because that's what the MA model is doing. Moving average. So think of average. All right, and then lastly, remember that the coefficients here need to add up to less than 1, and so when we have a greater lag model, so let's say we have an MA4 model instead of MA1 model, then we have a less volatile data, so it will be even less. There will be even less correlation, and the data will be very reverting around the mean. So like compared to this model where we have a little upwards of trend, it will be like right here, like spikes like this. If we have a higher Q value, because we have more lags that represent the model. And so if we have an MA1 model, we'll have very significant and clear correlations. Well, I want to say very clear because this is still an MA model. But compared to the MA1 with the MA4, the MA4 will even have less visual correlations and be very mean reverting. All right, that's it for the MA model. Next video will be the part 2 of the cycles, where I will introduce the AR model.